the thin film on top, if you make them epitaxially grows, then basically this is something you have. This is epitaxial thin film. So if you look at the in-plane, they will have one-to-one correlation. But however, there is one disadvantage is that once you decide or you choose a specific single crystal substrate, there's nothing you can do to change the patterns. So we hope that alternatively, what we can essentially do is that we want to control the alignment of orbitals. So we hope that in some area, we want some of the main, for example, dz square orbitals lining along the R-plane, and in the certain area, we want to make it, lying down in the plane. This is the ultimate structure we want to do. Then let me show you step by step. Okay, so start with, then I would like to show you the model system, which is bismuth ferrite. Okay, it's a classic but rarely seen room temperature multiphoric. So what is multiphoric? Basically, the material system composed more than 2 order parameters. So the take-home message is that for this material, all you need to know is that it's a ferroelectric and it's also anti-ferromagnetic. And please also remember that the 2 order parameters are coupled with each other. So that means when you try to rotate the correlation of the ferroelectricity, basically you will also rotate the anti-ferromagnetic plane. Okay, so this is the typical feature for this materials. So let's take a look at what we can essentially do. Okay, what we essentially do is that we have this epitaxial structure once again. We use the YBCO as a superficial layer. Then we put it into very light acid. We get a single crystalline freestanding film, which can be as thin as 2 nanometer, just 2 nanometer. And we put it down on exactly the same single crystal substrate, but this time, while we putting it down, we intended to rotate that for a few degrees. Okay, so this is so that we can control the twisting angle. And once you have this template, you do the growth once again. So let's take a look at what exactly happens. So please also try to believe us that we have extensive experience in growing complex oxide, including bismuth ferrite. So we do know if you grow the bismuth ferrite along 110 outer plane, okay? So basically you would have the stripe feature like this. Okay, so basically those stripe features are result from the elastic boundary condition. So you will see those kind of stripe pattern was strictly along 001 orientation in the plane. So if you look the area or the airframe or topography that we gain on the left side, the bismuth ferrite ground on the freestanding side. So you have the stripe pattern, that means the 001 orientation along this direction. So if you look at the right side, so you will see, oh, this is indeed another pattern or grow out along the other direction. So if you look at the interface, okay, so at the interface that we created, so you will find that, oh, this is indeed the rotation, okay, there's indeed a rotation according to what we designed. So of course, we can use this second method to double check that whether our assumption based on the stripe pattern or the AFM is correct. You can use the X-ray diffraction once again. So once again, along the R plane, they are 110 oriented crystalline thin film. So basically what you can have is 110 family of the diffraction. It simply tell you along the R plane, it's a single crystalline. But if you look at the in plane, and basically they have the twist angle, so you have the 2 set of the QFort symmetry. And you will also find that the twisted angle is around 85 degrees, which is exactly what we designed or what we observed through the AFM. Okay, so I hope now you have the picture that how to use this weapon. So basically, what we can demonstrate is that we not only rotate certain angle, we can rotate arbitrary angle. Okay, so here is a simple demonstration. If you follow the stripe direction, so this is the twist angle of 90 degrees. And so this is a twisted angle of 70 degrees, and this is also a twist angle around 90 degrees. So whatever angle you can create it. Okay, so the next question is that given that in Taiwan, we do a lot of silicon-related industry. So lithography is relatively easy in Taiwan, especially in academia side. So we start to ask ourselves whether we can try to configure different patents using the same approach. And hopefully, we can also control the alignment for the multiphoric materials. And the answer is actually yes. And when we can, the approach that we propose, it basically can be combined with conventional lithography. So in the end, basically what we can do is that we can properly control the direction of the population. So if you also use some special technique, for example here, this is the X-ray linear dichoism to reveal the antiferromagnetic axis, then you will see that it's indeed as we predicted, you want basically the AFM axis is perpendicular to the population. So according to this design, we can design some complex architectures. But you haven't come back to the original goal that we want to achieve, right? So remember that the ultimate goal is that whether we can fulfill the orbital or whether we can control the orbital alignment, something like this. So if you can achieve something like this, or if we can achieve something like this, they simply tell us we can create a spatial environment and we can make the, for example, the carrier that we care about, we make a spatial environment for they to wiggle in the environment. Okay, so the answer is basically yes. Then what we essentially do is that you pick up a substrate which is composed of 001 orientation, and on top of that, multiple stripes are composed of 110 orientation. But this is due to the gross nature. If you put the YBCO, which is also Hornbeck symmetry, so if you put it on the top, on the rectangular pattern part, the C-axis will lie down in the plane. And if you go the YBCO on top of the 001 orientation directly, you will find the C-axis along the outer plane. So this is the ultimate configuration you have. So we can essentially control the C-axis, then we can control the alignment of the dz squared orbital. So the representative orbital would be something like this. So lying in the plane, outer plane, lying in the plane, alternatively. So whatever the size, periodicity, or the spacing you can arbitrarily control. It can only depend on your lithography process. Okay, so this is a quick explanation. We basically use nail diffraction and come back and to look at the symmetry, whether it is expected as we design. Okay, so here I would also like to show you some result, but in this part I will use another model system, which is LSMO. If you still remember this LSMO, this is the sacrificial layer as proposed by the Berkeley team. But essentially, it's a colossal magnetoresistance system. So basically, if you do the resistivity versus temperature measurement, okay, so this is something you can have. If you don't apply any magnetic field, you will see a metal-insulator transition. But if you apply large magnetic field, you will see that the resistance drops dramatically. Then you will also see that the transition temperature goes to higher positions. You can try to calculate the change of the resistance. Then it can be quite high. This is why it is called colossal magnetoresistance material. All right, so let's go further a little bit. Then you see, this is to prove the capability of the method that we proposed. That basically we used 3 different systems to do the comparison. The first one is that we don't alter anything to the single-strate substrate. So you will only have the directly grown material on top. Okay, so this is the representative schematic for the orbitals. Okay, so in the second sample, in the inner area, we intentionally rotate that along in plane for 45 degrees. Okay, so you will see that the symmetry along the outer plane doesn't change, but along the in plane it does rotate for 45 degrees. But for the third sample, so we basically not only rotate in the in plane for 45 degrees, we also rotate that for 45 degrees along the outer plane. So this is something you can have. The schematic is something like this. So again, we use the X-ray diffraction to tell this is exactly happening in the system. So let's take a look at the transport behavior. So basically, this is the ground sample. If you do the magnetotransport at low temperature, and basically the magnetoresistance for this material system is pretty low. Okay, it's pretty low. But if you go to the second sample, that means that you create a 45-degree rotation and a grain boundary in between. Okay, so this is basically what you can see. You can see enhanced magnetoresistance. So I'm sorry that I don't have the time to go into very detail, but basically it follows a spin polarized tunneling model. So when you increase a nice and sharp grain boundary in the materials, and basically in CMR materials, you can observe something like this. But for the third sample, not only rotate in the in plane, but also rotate that along the out plane. So this is something you can have. So not only we can observe this kind of enhanced magnetoresistance, we can also find that this hysteresis-like behavior. And simply because that you rotate the system a little bit, when you apply the magnetic field, you effectively create and magnetic inhomogeneity. So this is the result to briefly explain the reason for the hysteresis.